Year 13, Mechanics, Moments, Lesson 2. We're going to look at equilibrium in today's lesson. Now, previously, when we have solved problems involving the particle model, for a particle to be in equilibrium, there must be a total resultant force of 0, i.e. the forces acting on the particle must be balanced. Now, if we're now considering a rigid body model, for a rigid body, such as a rod, to be in equilibrium, there are now two conditions which have to be satisfied. One, the total resultant force has got to be equal to 0, i.e. forces must be balanced as previously, but also the moments must be balanced, i.e. the total clockwise moments must be equal to the total anti-clockwise moments, which of course means that the total sum of the moments must be equal to 0. Let's have a look at three scenarios which will hopefully illustrate this a little bit further. So, look at the first diagram. We'll call this scenario 1. Now, let's have a look at the forces first of all. So we can see that the total force acting downwards is 15 newtons. The total force acting upwards is 15 newtons. So we can see that the resultant force is equal to 0. The total resultant force is equal to 0. Now, let's take moments. In each of the three scenarios, we're going to take moments about point B for convenience. Now, that means in each case, we can exclude the force acting at point B when we calculate moments because it has 0 perpendicular distance from the pivot or the pivot point. So, let's take a look at the first scenario. Now, we can see that the force acting at A, imagine pulling down on it, will produce an anti-clockwise moment, and the force acting at C will produce a clockwise moment. Now, what are the values of these moments? So in an anti-clockwise direction, we have a moment of 5 multiplied by 3, which is 15 Newton meters. And in the clockwise direction, we have a moment of 10 multiplied by 6, which is 60 Newton meters. So we can see here the total clockwise moments and the total anti-clockwise moments are not equal to each other. So this situation here, we do not have equilibrium in example 1. Although the forces are balanced, the moments are not. Let's take a look at the second diagram. Now, in this case here, we can see we have total downwards forces of 10 newtons, total upwards forces of 7 newtons, which means that the resultant force is not equal to 0. So that will stop this situation from being in equilibrium. Let's have a quick look at the moments. So we know we're going to take moments about B. So again, B is the pivot point. The 8 Newton force produces an anti-clockwise moment of 24 Newton meters. And the 2 Newton force produces a clockwise moment which is 24 Newton meters. So again, moments are balanced, but the overall resultant force is not 0, so this situation, this system is also not in equilibrium. Let's take a look at the third scenario down here. Now, downwards we have a 4 Newton force and a 2 Newton force, so 6 newtons acting downwards. And we have 6 newtons acting upwards. So resultant force, if we balance the forces, is equal to 0. So we're fine on that count there. Now, what about moments? Let's have a look at the two forces. So there's an anti-clockwise moment about point B produced by the 4 Newton force at A. It's 4 multiplied by 3, which is 12 Newton meters. Now there's a clockwise moment produced by the 2 Newton force at C. The magnitude of this clockwise moment about the point B is 2 multiplied by 6, which is also 12 Newton meters. So we now satisfy both conditions. We can see that the resultant force, the total resultant force is 0, so the forces are balanced, and the total anti-clockwise moments equal the total clockwise moments when moments are taken about a particular pivot point, which means that we have in situation 3 a system that is in equilibrium. Now, what would happen in the other two situations? In the first example, because the forces are actually balanced, the whole rod or rigid body isn't going to move upwards or downwards, but it will rotate because there is an overall moment of 45 Newton meters in a clockwise direction. It will start to rotate in a clockwise direction. Now, in the second system, the total anti-clockwise moments equals the total clockwise moments. Moments are balanced, so it will not rotate. There will not be a turning effect. But because there are 10 newtons acting downwards and 7 newtons acting upwards, there is a resultant force of 3 newtons downwards, and the whole rigid rod, the whole system, will move vertically downwards under the influence, under the action of this resultant force of 3 newtons. Let's have a look at some more detailed equilibrium problems. So we're going to read through the information and we are then going to sketch a clear diagram. So a uniform rod. Now, let's stop here for a second because this is a really important modelling word here. The fact that the rod is uniform means that the centre of mass of the rod is placed exactly halfway along its length. This is because if the rod is uniform, the mass of the rod is uniformly distributed along the length of the rod. Now, we know the rod has a length of 4 meters and a mass of 5 kilograms, and it's pivoted at a point C where AC equals 1 meter. We have 2 tasks here. We have to find the mass of the particle that must be placed at A so that we maintain equilibrium with the rod in a horizontal position, and we must also find the reaction force at C. So questions like this can seem a little bit overwhelming to begin with, so it's really important that we sketch a clear diagram and make sure that we understand exactly what the system looks like. So here is my uniform rod, and it's AB, so one end of the rod is A, one end of the rod is B, and I'm actually going to write AB equals 4 meters by the side here, because if I add this to the diagram too quickly, it sometimes becomes a bit unclear. Now, the rod is pivoted, so let's draw in some sort of pivot there at a point which is C, and here we know that AC is equal to 1 meter. So what I might do is now draw in the distance B to C, which of course is 3 meters. Now, forces acting. Remember, the rod must have a weight of 5g, and because it's uniform, the weight of the rod is going to act halfway along the length of the rod. So we've got a weight here, which we're going to add to our diagram, which is 5g. Because the rod is pivoted at C, there will be a reaction force of the pivot pushing up on the rod like that. Now, what other forces have we acting? Well, we were told that there is a particle that is placed at A. Let's draw it on there, so it's positioned at A. And we don't know what the mass of the particle is, so we don't know what its weight is. So the weight of the particle is going to be mg. So here is all of the information. Now, what are we going to do? Well, the first thing is to think about the fact that we want the system to be in equilibrium. Now, that means we need the forces to be balanced. So the first step here is to think about the forces. Now, what forces do we have acting? We have R acting vertically upwards, which has got to be balanced by mg plus 5g, both of which act downwards. So that's the first thing that we need to consider, balancing the forces. The second thing that we need to consider are the moments. And that means we need to take moments about a particular point. Now, you can take moments at any point along the rod, but think strategically. Remember, if there is a force acting at a particular point that has 0 perpendicular distance from that point, it has 0 moment about that point, which means you can eliminate a force from a calculation. So it makes perfect sense to calculate moments about point A, because that would eliminate the green force there, the weight of particle A. Or alternatively, it makes a lot of sense to take moments about point C because we then eliminate the force R. It would make very little sense to take moments about point B, for instance, because we then end up with an equation that contains two unknowns because both R and mg will be involved in that equation because they will both have a moment about B. So I'm going to choose to take moments about point C. Up to you as to whether you do this or whether you have a go at taking moments about point A and seeing if you get the same answer. You will. So taking moments about point C, well, we know that the weight will have a clockwise moment of the rod and the weight of the particle will create an anti-clockwise moment. So remember, if the system is in equilibrium, our total clockwise moments equal our total anti-clockwise moments. So what are our total clockwise moments? Well, we have the weight of the rod, 5g, multiplied by the distance from the pivot C, which is equal to 1 metre. And this must be equal to the weight of the particle, which is mg, multiplied by its distance from the pivot, which is also 1. And this very simply gives us the mass of the particle as 5 kilograms. Now, what can I do with that information? I can substitute that information into this equation over here. I've highlighted it in yellow, and that tells me that R, the reaction force at C, is equal to mg plus 5g, which is, of course, 10g newtons, or 98 newtons. Let's have a look at a second example. We have two children sitting on a non-uniform plank. Now, this is important, another modelling term here. The fact that the plank is non-uniform means that the mass will not be evenly distributed along the length of the plank, which means that the centre of mass will not be exactly halfway along the plank. Now, the plank has mass 2 kilograms, length 2 metres. It is pivoted at the midpoint. The centre of mass, however, is at another point C. Now, two children are sitting on the plank. One of them is sitting at the point A, and the other one, all we know is their mass. So, what do we have to find out? We have to find out where Veronica has got to sit for the plank to be horizontal, and we also have to find the size of the reaction force at the pivot. So, the fact that the plank is horizontal means we're looking at a balance or equilibrium situation. It's a seesaw question. So let's draw a really clear diagram to represent all of this information. So I'm going to start off with drawing my non-uniform plank here. So it's AB, and again I'll just write down by the side that AB equals 2 metres. Now the plank is pivoted at the midpoint, so let's mark on that midpoint, which I believe is called M. And we know that that's halfway along, so that's 1 metre, and this distance from here to here is also 1 metre as well. Now, what else do we know? We know that Archie has a mass of 24 kilograms and sits at A. So here's Archie, and this means there's a force, which is Archie's weight, of 24g at point A. Now, there's a reaction force acting vertically upwards here for the pivot pushing up on the rod. And then the last piece of information we know is that the centre of mass of the plank is at C, where AC equals 0.8 metres. Now, what does this mean? That means that at this point C, where the centre of mass is, this is where all of the weight of the rod of the plank appears to act. So all of the weight will always appear to act at the centre of mass or the centre of gravity. Now, the mass of the plank is 2 kilograms, so that means the weight of the plank is 2g and acts at that point C. Now, Veronica, we know she has a mass of 30 kilograms, but we don't know where she's sitting. So we just have to place her on the diagram. Now, people often worry about this because they don't know where to put this extra particle. It doesn't matter because ultimately the question will work out in the end. I'm going to place Veronica over here. And let's draw in her weight, which is 30g. Now, I don't know how far she is from B or from C, from A or from M. I'm going to say Veronica is X meters away from M. Again, I could take that measurement from B. Everything can be worked out relatively. You can try this question in lots of different ways and you will still get the correct answer at the end. So, remember what we did last time? We looked at balancing forces. So, forces acting upwards, we have R. That is the only upwards vertical force. And we know that that has got to be balanced by 24g, 2g, and 30g acting downwards. So we've solved the second part of the question here. So the reaction at M is equal to 764.4 newtons when we balance forces in the vertical direction. So one part of the question already answered. Now, let's have a look at moments. Now, you've got to choose a pivot point about which you're going to take the moments. And really, in this situation, it's very easy to take moments about most of the points on the rod. Ultimately, if you take a moment about a point at which a force is acting and there's no perpendicular distance from that pivot point of that force, you will eliminate that force from your calculation, which may make the situation a little bit easier. I'm going to take moments about point M. So in yellow, I'm going to mark on the direction of each of the moments produced by the other forces. So Veronica's weight, 30g, imagine pulling down on that like a string. Everything would start to rotate in a clockwise direction. That's a clockwise moment. 2g, pulling down on that force would cause everything to rotate in an anti-clockwise direction, and the same with the 24g force. So really important to identify the direction of each moment. So if the system is in equilibrium, remember, our total clockwise moments are equal to our total anti-clockwise moments. Using a little bit of shorthand here just for speed. So clockwise, we just have the 30g and it's multiplied by distance x. Anti-clockwise, well, we have 2g. Now, what's the distance between C and M? It's got to be 0.2. And then we have the weight of Archie, which is 24g multiplied by the distance between A and M, which is also 1. Now, this is a really easy equation to solve. Hopefully you can all see that g actually cancels out of every term, which makes life a little bit easier as well. So from here, let's work out what x is equal to. And it comes to 0.96 meters. So how do we express this answer in a way that refers back to the original question? We can say that Veronica sits 0.96 meters to the right of M. Or you could say she's 0.04 meters from B. Now, depending on where you placed your measurement x, of course, you would get a slightly different answer to this question, but it would all fit back in with the information in the question. Now, if you had placed Veronica, let's say over here instead, force of her weight would have looked like this. And if you took moments about M again, well, like the 2g and the 24g Newton forces, this would produce another anti-clockwise moment. And what you would find is when you did this calculation, your value of x would work out to be negative 0.96. Now, that doesn't mean you've done something wrong. It just means that actually she should be placed on the other side of the pivot. So if you have to make an estimate or a guess as to where you should position a distance in a diagram when you're solving one of these problems, it honestly doesn't matter. I mean, it was logical in this question that Veronica would have to be on the other side of the pivot, otherwise the whole thing would likely have tipped over. So it did make sense to place Veronica closer to B. But equally, we could still have got the correct answer at the end, as long as we could interpret a negative answer correctly. Why don't you have a go? Place Veronica in a different position and see what happens. Example 3. So we are back to a uniform rod, which has got length 5 metres, mass 30 kilograms. Now it's resting horizontally. That means it's in equilibrium, and it's on supports at C and D, where we're given this information here. Now we're told that a man of mass 75 kilograms stands on the beam at point E, and we're given some information about the distance AE. So what do we have to do? We have to find the magnitude of the reaction of each of the supports on the beam. So make sure you've read through all of that information a few times so you are fully clear about what this means. Let's start drawing the diagram. So here's our uniform rod, AB, and I'll write by the side AB equals 5 metres. So it's got a mass of 30 kilograms. Now because it's a uniform rod, this means that the weight of the rod will be in the direct midpoint, or at the direct midpoint of the rod, acting at the direct midpoint. So we can draw in that 30G force there, which is the weight of the rod. Now, AC equals 1 metre. So there's a gap of 1 metre to a support at C. And we'll draw in the reaction force of the support at C pushing up on the rod. And we know that BD is also 1 metre, so something similar over here. Now, we know that the measurement from here to here has got to be 2.5 metres, halfway along the rod. And we know that a man of mass 75 kilograms stands on the beam at E, where A to E is 2 metres. So that measurement there is 2 metres, and there's the man's weight, 75G. So let's find the values of RC and RD. So first job, we know we want the forces to be balanced for a system that's in equilibrium. So what do we have? Acting in an upwardly direction, RC and RD, and they have got to be balanced downwards by 30G and 75G. So what does that tell me? I can simplify that to RC plus RD equals 105G. So at the moment I have an equation with two unknowns. Unknown until we start having a look at calculating moments. So where could I take moments? Well, again, I can take moments at any point. But if I take moments about a point like C or a point like D, I automatically eliminate the forces acting at those points, RC or RD, and that makes the equation much easier. Whereas if I took moments about point A, I would end up with an equation that featured RC and RD. Now that's not a problem. I'd have simultaneous equations. I could solve it with my other equation that I've highlighted in a rectangle here. But why not make life easier for ourselves? Let's take moments about point C. Now, first thing, I am going to draw on the direction of the moment of each of the three forces. So the 75G force, pull down on it and we will get a clockwise moment. The 30G force about point C, so remember you're pinning point C down. Imagine pulling on the 30G force, think about the direction everything would move in. It would be a clockwise moment. And then RD, on the other hand, would be an anti-clockwise moment. So we know our total clockwise moments must equal our total anti-clockwise moments. And we know that moment is equal to force multiplied by distance from the pivot. So in a clockwise direction, what do we have? We have 75G multiplied by a distance of 1 metre from C, make sure you can see why that is, plus 30G multiplied by a distance of 1.5 metres from C, and these are balanced by the force RD which is a distance of 3 meters from C. It can sometimes be a little bit difficult to see those distances, so go back, make sure you can work out why they are the values they are very carefully. Now, the force RC, of course, is acting at C, so it has 0 perpendicular distance from C, the pivot, 0 moment, so we can exclude that. So this is now very easy. We can work out the value of RD, and it comes to 392 newtons. Now, we can substitute back into this equation over here, and this will give us our value of RC, which is equal to 637 newtons. Now, it's interesting to pause here for a minute and look at the fact that RD, 392 newtons, is a lot less than RC, which is 637 newtons. Now, can you think about why that is? And hopefully, if you realised, it's due to the fact that the man is a lot closer to C than he is to D. And as a consequence, the pivot at C effectively has to push up a lot harder to make sure that equilibrium is maintained and the rod remains horizontal. So we're going to finish this lesson off with a few additional, slightly different types of example. So the first one of these is an example about a laminar. Now, a laminar is a flat, plane object with a negligible thickness. So think of a piece of paper, something that essentially has an area but has such a small thickness in comparison to its area that we can ignore the thickness when we're using it for a model. So a sheet of cardboard, a sheet of paper could be modelled as a laminar when we're dealing with a mechanics problem. Let's have a look at this question. So figure 7 below shows a rectangular laminar, ABCD, with sides AB of length 60 centimetres and AD of length 50 centimetres. The laminar is lying flat on a smooth horizontal surface and is acted upon by the following 5 horizontal forces. So you can see a list of 5 forces here, 2 of them X, Y unknown, and all 5 of them drawn on the diagram. Our task is to calculate the values of each of the following, X, Y, and the distance D marked on the diagram. Now, it's up to you as to whether you want to pause at this point here and have a go at the question yourself and then check your answer, or if you feel you need a little bit more support, you can work through the problem with the video. Now, this is exactly the same as the rigid body type problems you've been solving. We need to look at balancing forces and we need to look at balancing moments. So, forces first of all. Now, we have forces which are in this direction, vertical, which must be balanced. What do we have? We have Y acting upwards, which is balanced by 40 and 27 downwards, so instantly I can work out the value of Y as 67 newtons. What forces do we have acting horizontally? I have 45 and X balancing each other. So I've worked out X and I've worked out Y. Now, let's think about moments. Where could we take moments about? Where would be a good pivot point? Now, I want to calculate the distance D. So in order to keep my calculations a little bit simpler, I am going to take moments about the point A. But you could do this question in multiple ways and you will still get the same answer. So we're going to take moments about point A. So that's interesting because look at that. At point A, we have this force here, Y, and we have this force here, 45 newtons. They both have 0 perpendicular distance from A, therefore they have 0 moment about A, and we can exclude them from our calculations immediately. Now, what about the other forces and the moment produced by each of these in the direction? Well, I'm going to highlight this one first of all, 40 newtons. Now, what is its perpendicular distance from A? It is not 50 centimetres because that is not the perpendicular distance. That's the distance in line with A. So this is interesting because this green force here has 0 perpendicular distance from A, because it's a vertical force, which means its perpendicular distance would have to be a horizontal measurement. So 40 Newton force has 0 moment about point A. So we can exclude that from our calculation. So this leaves us with the other forces. Now, what about this one here, X, which I've highlighted in red, which we now know is 45 newtons. If I pull on this, what direction will the system move in if I pin down point A? Well, try it with a piece of paper, hold it flat, pin down a corner, pull on a point like that, and you will see that this would be an anti-clockwise moment. So remember, our total anti-clockwise moments must be balanced by our total clockwise moments. So where are we going to get a clockwise moment from? Well, this force here, the 27 newtons. If I pull down on it, the whole system will rotate about point A in a clockwise direction. So our anti-clockwise moments, we have 45 newtons. Now, because this is a horizontal force, its perpendicular distance from A has got to be its vertical distance from A, which is D. So 45 multiplied by D. Be very careful. It'd be very easy to try and do 45 times 60, but 60 is not the perpendicular distance. The force is horizontal, so you're looking for a vertical distance. And similarly, with the 27 Newton force, it's a vertical force, so when you're looking for its perpendicular distance from A, you're looking for a horizontal distance from A, which is 60. Very simple equation to then rearrange, and you will find that D works out to be 36 centimetres. So let's have a look at the concept of levers. Now, a lever is something that can be used to lift or move a heavy object using a relatively small force. And levers depend on moments for their actions. Essentially, think about it, if you can apply a force over a larger distance, then you will create a larger moment. And it's the effect of the moment, the turning effect of that force, that then allows you to lift or move that heavy object. So we're going to consider two common types of lever. In both cases, a load W. So here's the weight of the object in both examples, is being lifted by an applied force F. So in both cases, the force F is going to be applied. So in the first diagram, the force F will be applied like this. And in the second situation, the force F will be applied like that, a pull versus a push. Now, the difference between the two systems is the position of the pivot. In the example on the left, the pivot is at one end of the lever, and in the example on the right, the pivot is within the body of the lever. Now, what is the other piece of information we're missing? The lever has a length of L, like so. Now, let's go from each example. So in both cases, we're going to take moments about the pivot, which we'll call P. Now, the system is in equilibrium, so that means that the moments must be balanced. Let's have a look at the diagram on the left-hand side. So this force F is going to produce a clockwise moment. This force W is going to produce an anti-clockwise moment. We know total anti-clockwise moments equal total clockwise moments. Moments are balanced. So we know if we call this distance here x, that W multiplied by x is equal to F multiplied by L. And this then tells us that the applied force F is equal to W multiplied by x over L. And I'm just going to rewrite this as W multiplied by x over L, and you'll see there's a reason for this when we look at the situation on the right-hand side. So taking moments about P again, I'm going to say that this measurement here is x. So let's look at the two forces. F is going to produce an anti-clockwise moment, W is going to produce a clockwise moment. So we know that F multiplied by, now the distance between F and P is this measurement over here, which is L minus X, and that is equal to WX. So rearranging this gives me my applied force F is equal to WX over L minus X, which I'm going to write as W multiplied by X over L minus X. Now let's have a look at the significance of these answers. Let's go to the first question here. So we can see that F is equal to W multiplied by X over L. Now think about the fact that X is a lot smaller than L. Now this then tells you that X over L has got to be a value that is less than 1, which tells you that F is going to be smaller than W. So the force you apply is going to be less than the weight of the object. And that's the whole point of a lever. It allows you to lift this heavier load by applying a smaller force, using the turning effect of the force, using the moment to help you work. Let's do a similar analysis of the second example. So again, we have F, which is equal to W multiplied by X over L minus X. Now, providing that the pivot is nearer the end where the load is, then the applied force is going to be less than the load. So that's dependent on your pivot being closer to the load. Now, if X becomes larger, i.e. the pivot moves closer to where your force is being applied, then there is a danger of X over L minus X becoming a number that's too large, and this will make F too large. So let's have a look at a slightly different concept, a couple. Now, a couple is a set of forces which have a zero overall resultant but a non-zero total moment. So let's look at the diagram below to illustrate this. So I've got a 12 Newton force over here and a 12 Newton force over here. I'm going to pivot my rigid body here at this point over here. So that then allows me to calculate some moments about this point. Let's put in some distances. So the distance here is 5 meters and the distance here is 10 meters. Now, let's have a look at the information in the question. We have 12 newtons acting downwards, we have 12 newtons acting upwards, which means that the total resultant force is 0. So the forces are in fact balanced. Now, what about the moments? Well, let's take moments about this point P. So looking at the two forces, pinning down point P, imagine the force on the left, the 12 Newton force, it's going to produce a clockwise moment like this. And what about the 12 Newton force on the right, pulling down on that? It's also going to produce a clockwise moment. So taking moments about P, we have a 60 Newton metre clockwise moment produced by this force and a 120 Newton metre moment produced by this force also clockwise. So the total overall moment is not 0. It's equal to 180 Newton meters in a clockwise direction, which means the system will rotate or start rotating in a clockwise direction. And this is what we would call an example of a couple. It satisfies both conditions. We have 0 resultant, but we have non-zero total moment. And a couple will result in a rotation of the system because the moments are unbalanced.